Hello. In this video we're going to finish section 1.3. Okay. And we'll start with the definition for a linear combination of vectors, So here's the definition. A linear combination of vectors v1, v2, v sub n, and Rn, so this could be any dimensional space, so n-dimensional space, so it could be a vector in 2 dimensions, for example 2, 3, or a vector in 4 dimensions, 2, 2, 3, 4, right? Okay, so here's how we define a linear combination of vectors v sub 1 through v sub n. This is the linear combination of vectors v sub 1 to v sub n, okay, where c1, c2, cn are scalar. Scalar means they're a number. They're not a vector, okay? So, for example, a linear combination, let's say I have two vectors, u equals 3, 2, 1, and v equals 3, 3, 2. Then a linear combination of these two vectors, I can say, for example, w equals 2 times u minus v, for example. This is one linear combination of u and v, and this would equal 2 times 3, 2, 1 minus 3, 3, 2, which equals, now for multiplying a vector with a number, I just multiply. So I'll get 6, 4, 2 minus 3, 3, 2, which is 3, 1, 0. I just subtract each one. Okay? So this right here is a linear combination of these two vectors right here. Okay? And what is a linear combination? It means I multiply one vector by some number, and I multiply the other vector by some number, and then I add them. Okay? Another linear combination would be 3u plus 7v. This would be another linear combination of u and v. And if I had u, v, and w, let's say, or let's say p equals 1, 1, 0, okay, and then I had plus 5p, this is a linear combination of u, v, and p. Okay, that's how we define linear combination. Okay. Now, let's say I had the vector v1 and the vector v2. Okay. And let's say v1 is negative 1, 2, and let's say v2 is 1, 1. Okay? And let's say I wanted the point up here. The point is 2. Five, let's say. Okay? And this is a vector w. Well, notice something. Notice that I can take v1 and I can add 3 times v2, and what I will get is negative 1, 2, plus 3 times v2 will give me 3, 3, which equals 2, 5. So this equals w. Okay? And actually, for these two vectors v1 and v2, any point I choose in R2, this is R2, right, two-dimensional space, any point I choose in R2, let's say this point here, I can represent this vector here, as a linear combination of v1 and v2. How? Well, I would have to find these 2 points here, these 2 weights here, or scalars, to multiply each one by these values so that I can get the actual linear combination. Now, I'll show you how to find that actually, the linear combination, by way of example. Okay? So let's say I had the vector a1 equals 1, negative 2, negative 5. a2 equals 2, 5, 6. And b equals 7, 4, negative 3. And I ask, is b a linear combination of a1 and a2? If yes, find the linear combination. Okay? Well, you should immediately notice or recognize that if b is a linear combination of a1 and a2, then b would need to equal some value times a1 plus some value times a2. So some number x1 times the vector a1 plus some number x2 times the vector a2. Right? And this would be x1 times 1, negative 2, negative 5 plus x2 times 2, 5, 6, which would equal x1 negative negative 2 times x1 negative 5 times x1 plus 2x2, 5x2, 6x2. Okay? And when I add two vectors like this, I know that I just need to add these two, I need to add these two, and I need to add these two. So what I'll end up getting is x1 plus 2x2 negative 2x1 plus 5x2. negative 5x1 plus 6x2. Okay? And so, what is the question asking me? The question is asking me, does b equal some x1, x2, some x1 times a1 plus some x2 times a2? And if yes, it's asking me find x1 and find x2. Okay? And so here I have b equals this formula. So b is 7, 4, negative 3. And I'm asking, does it equal this matrix here where x1 and x2 are numbers? And if yes, I need to find x1 and x2. So you should immediately recognize that this gives me three systems of linear, or it gives me a system of three linear equations. 7 equals x1 plus 2x2. 4 equals negative 2x1 plus 5x2. Negative 3 equals negative 5x1 plus 6x2. And what am I being asked? I'm being asked, again, to find x1 and to find x2, such that this is true. Do we know how to do this from previous sections? Yes, we do. This is a system of equations. 3 equations, 2 variables. Okay? So immediately you should recognize that I can make this into a matrix with x1 here, x2 here, and the number for b here. I make my augmented matrix, so I'll get x1 is 1, negative 2, negative 5, and then I have 2, 5, 6, and then I have 7, 4, negative 3. And I just solve this. I row reduce. Okay? And when I row reduce this, I end up getting the following. 1, 0, 0, 1, 0, 0. And then I have 3, 2, 0. What does that tell you here? It tells you that x1 equals 3 and that x2 equals 2. So, is B a linear combination of these two vectors? This is the same thing as asking, does this system of linear equations have a solution, at least one solution? And yes, it does. And so I have B equals 3 times A1 plus 2 times A2. And you can check this if you'd like by plugging in A1 equals 1, negative 2, negative 5. And A2 equals 2, 5, 6. And multiply this by 3, multiply this by 2. Add them, and you should get the value, the vector for B, which is this right here. Okay? So, now we've learned how to represent a system of linear equations, actually, using an equation with vectors in it. You see? So now we can formulate questions involving vectors to questions involving matrices and systems of linear equations. Okay? So this gives rise to the following theorem. a vector equation b equals x1 a1 plus x2 a2 plus dot 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 plus xn an. This vector equation has the same solution set, and the solution set means the values for x1, x2, all the way to xn, or the different values that it could be. It could be, for example, you could have more than one set of x1, x2, all the way to xn, such that this formula is true. Okay? So this vector equation here has the same solution set as the augmented matrix you make the columns of the matrix the vectors of your vector equation. So a1, a2, dot, 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 an, and then the augmented part is b. Okay, and we already saw that here. We saw this vector equation here, and we saw that the solution, which was x1 and x2, is the same as the solution for this system of linear equations, which is the same as the solution for this augmented matrix, where this column here is a1, this column here is a2, and this column here is b. Okay? So the proof for this theorem is something similar to this argument, this algebraic argument I presented here. Okay. Now let's define something else. The spanning set of, let's say, vectors v1 all the way to vn is represented using this notation here. And is the set of all linear combinations of v1, v2. The set of all linear combinations of v1 and v2. That is the same as the set of all vectors b, which can be written as c1 v1 plus cm vn. Okay? So basically, I can say that b is in the span of v1 to vn if and only if b is a linear combination of v1 through vn for some c1, c2, cn. Okay? So we can think of the two-dimensional example, and I'm sure you've taken, if you've already taken physics, then you've taken this already. Okay. If I have the vector I hat, which equals 1, 0, and I have the vector j hat, which equals 0, 1, any vector I choose in R2 can be represented as a linear combination of I hat and j hat. Okay, so in this case, if this was 3, so here, if I have this here, which is 3, 2, well, this vector is nothing more than just 3 times I hat plus 2 times j hat. Okay, if you look, this vector right here, this vector is 3 I hat, and this vector here is 2 j hat. Okay, now again, I can take this vector and move it over here. I can take 3j hat and move it right here. This is 3j hat. Okay, and we remember that vector addition, in vector addition, what I will end up getting is, so I have from the beginning to the end, and then from beginning to the end, so I have this vector right here. This is the vector 3j hat plus 2 I hat. You see? So basically, any number, or I'm sorry, any vector, any point in R2 can be written as a linear combination of I hat and j hat. So therefore, the span of I hat and j hat is all of R2. You see? Okay. So this should tell you, you should immediately think to yourself, okay, what if I have just one vector? What if I have, let's say, the vector here, v, and then I have another vector that's on the same line as v, but it's right here, u, and u equals 2 times v. Then what will the span look like? Well, the span of v and u, in this case, if v equals 2 times u, or I'm sorry, if u equals 2 times v, then the span is any linear combination of v and u. So for example, if I have v plus 3u, well, this is v plus 6v, which is 7v, which is going to give me this vector right here. Okay? If I have v minus 3u, this will be v minus 6v, which is negative 5v, which will give me this vector right here. So what is the span of u and v? It's the set of all linear combinations. And we see that any linear combination of u and v will be on this line right here. Okay? So the span here is just a line, geometrically. But in this case here, I can never say that j hat equals some number times I hat. This is not true. So, if for two vectors, if they are not a multiple of each other, then the span of those two vectors is a two-dimensional space R2 if the two vectors are exist in 2 dimensions. Actually, any two vectors. If the two vectors in 3 dimensions or in 4 dimensions are not a multiple of each other, then the span of these two vectors is R2. So then you should think to yourself, what will give you the span equals to R3? A whole, not just a plane, but a 3-dimensional space. And we saw that if V is a multiple of U, or vice versa, then the span is going to just be a line. Okay? And this is true for not only vectors that exist in 2 dimensions, like this one here, but for 3 dimensions and 4 dimensions, and so on. Okay? Okay, so now I can give you what you should do is on your own, you should do the following homework. And I will assign this homework on Teams. Okay? And I'll upload another video doing a little bit of review for section 1.2 and 1.3, going over some of the homework problems. I'll set up a live review session sometime this week, maybe on the 15th, for sections 1.2 and 1.3, and maybe also the next section which I'm doing, which is going to be 1.4. And then you'll have a quiz next week, maybe on October 20th or October 22 or something like that. We'll have a quiz. Okay. If you have any questions about the homework, please contact me. This homework will be due on the 8th. I'll make this homework due on the 18th of October.